Let's welcome, please welcome Felix.
Okay, thank you very much for the invitations. I hope you can hear me.
Yes.
Yeah, okay, thank you for giving me a chance to talk here. And again, sorry for not coming. It's always hard to travel overseas with 2 young children at home, but it would, would have been a nice thing to escape Britain at this time of the year. But yeah, in any case, so I want to give you a bit of a progress report on the Columbus program system. So basically what Columbus is, it's a collection of high-level multi-reference programs. And when you want, if I should pick out 2 things that Columbus does really well, then one is the idea that there's an uncontracted MRCI with parallel implementation, and you can use it for open shells, for radicals, for excited states, generally for systems with difficult electronic structure. And then there is gradients, non-adiabatic couplings, and spin-orbit couplings at the MRCI level. And that's why you can use it for dynamics or for spin-vibronic processes in a more general sense, where you have non-adiabatic interactions, but also spin-orbit coupling. So today I want to talk a bit about Columbus as such, and then give you 2 kind of case studies. One is about unpaired electrons in polycyclic hydrocarbons. Those are static calculations. And then I want to talk about how we do dynamics. So the idea what we do in Columbus is we have this uncontracted MRCI that allows you to treat static and dynamic correlation on the same footing. So basically when we do multi-reference computations, and I'm sure that's what many of you do, is first you define, you divide the orbital space, you have the frozen core orbitals that you ignore, you have the active orbitals up here, that's where you build your reference space, where you can run your CASSCF computations, and then you have excitations from reference into active and active into external orbitals. So then what you realize is when you do this, when you have a correlated multi-reference theory, is that you can make all these different kinds of excitations. You start out with a reference here. Of course, this is just a toy space with three different references, but then you can see you have all these different excitations. And the problem is that this is not unique. For example, this one is drawn as an excitation from the doubly occupied one into the active space, but you could, for example, also construct this one as a double excitation from here. So the problem is that when you do multi-reference theory, there's no unique assignment as single and doubly excited. And for coupled cluster, that's the one thing that really destroys multi-reference coupled cluster. That's why it's so hard to do multi-reference coupled cluster, because you have all these excited computations and you don't know how to count them when you try to to get disconnected excitations. The nice thing for uncontracted MRCI is that you just kind of use all of them at face value, so you don't have to worry about anything else. So for example, also when you do contracted MRCI, then you kind of have to separate between single and doubly excited. So that's kind of the nice point here, that this method is very simple and you kind of get what you ask for. Then what else does Columbus do is that Columbus uses the graphical unitary group approach. So on the one hand, that's a way to enumerate all these configurations so you kind of have a clear idea how the CI vector structure, and it also allows you to evaluate the coupling elements. So you do this in spin adapted configuration state functions, and then if you have lots of open shells here, lots of open shells here, then it's usually not so clear how to evaluate any coupling elements. So the nice thing is, with uncontracted MRCI, it's a straightforward formalism. There are no ambiguities, and that's why you can also get gradients, non-adiabatic couplings, and spin-orbit couplings easily. The downside is, of course, you generate a large number of configurations. When you compare it to any internally contracted method, then the number of configuration, scales with the size of the reference space of kind of the CAS active space, which means that the CI vector is going to be longer. But what do we do here is that we just have this efficient parallel MRCI computation, and 1 to 2 billion configurations can be treated routinely. Higher things are possible. So in that way, we can get very far with MRCI. All right, so the one bit of news about Columbus is that Columbus is now released open source under LGPL. So we're kind of motivated by Open-Sourece, kind of following the path of Open-Sourece to have an open source release. There's also continuous integration and testing to manage collaboration easily. I am still providing binary releases because that's what people seem to want to know. And of course, I want to say that contributions are very welcome. I mean, everyone can get the code, get a fork, and start playing around with it. So if you're interested, please take a look. So then I want to go back and talk to you a little bit about the kind of science that we can do with Columbus. So the first thing is it's about polycyclic hydrocarbons. So the idea is that, of course, they're part of graphene building blocks. And it turns out that their properties are highly tunable depending on how big they are, what kind of shape for the edge you use. So, but one thing, and 10 years ago, that was actually very contentious. So we had to fight about that a lot. But now everyone kind of accepts this, that if you make these systems bigger, then you have open shell character emerging, and that's why you need multi-reference computations. And here again, I'm suggesting use MRCI or as size extensivity corrected version, at least approximate extensivity correction, where we can describe static and dynamic correlation. So the story started here about 10 years ago. We look at the graphene nanoribbons shown on the right here. We just make them longer and longer and longer. Then we do this MRAQCC, so it's MRCI with extensivity corrections. And then we see how the wave functions change. And what we plot are the natural occupation numbers. So you can see for the first one, that's the one that's shown here in black. So we have kind of a zigzag edge that's 2. So that's kind of 3 naphthalene molecules glued together. Then we see down here, we have a very low occupation close to 0, very high occupation close to 2. So this molecule of 3 naphthalene glued together, that's more or less a closed shell molecule. Then we add one more ring, so we have 3 anthracene molecules next to each other, and you see kind of that the occupations of these 2 orbitals are already close to 1, and then for any longer ones, we have occupations of natural orbitals close to 1, and an occupation of a natural orbital close to 1. That means that means that you have a biradical formation. So when we make these molecules bigger, we get biradicals. And now we kind of have this number of the unpaired electrons. We want something to kind of watch all the unpaired electrons. So what we do is we compute the density of unpaired electrons. So that's basically the squared natural orbitals weighted with this factor. And you can see that this factor vanishes if the occupation is either 0, so if the orbital is completely unoccupied, or the occupation is 2, so with a doubly occupied orbital. And then this is kind of a non-linear form that if we just have a little bit of occupation, things are just kind of cleared out, so we don't see all the dynamic correlation. Then, we use this, and for example, you remember that the small one I showed you, the 3 naphthalene molecules together, there's almost no unpaired electrons. And then if we make our system bigger, we get all these unpaired electrons, and we see they're located along this zigzag edge. And that's this one theme that keeps continuing. That is especially when you have these zigzag edges. Recall here, as opposed to these edges, that's where the unpaired electrons end up being. So just a point here, we find this trend for many different systems. So these colorful ones are different two-dimensional systems. We also find it for the polyacenes. That's the black line here. And as I said, it's almost 10 years ago, but at that time, no one believed us that polyacenes really have this polyradical character. And there was a lot, fighting around with referees. The only thing that's interesting is that if you do these molecules that are called phenacenes, so they don't have any zigzag edges because you change them around. Or in another way, they have lots of class sextets, so lots of happy benzene ring with sextets. And on these phenacenes, they don't form any kind of unpaired electrons because those are this more just stable systems where we have benzene rings and double bonds. So when you then the next thing that I wanted to say here that I think it's always a bit fascinating to me is that kind of how things change when you change the edge shape. So here again we have this large periacene molecule with unpaired electron density around here, and then we actually make the molecule bigger. We add another phenyl ring, but we add it here in the middle, and suddenly the unpaired electron density disappears. So here we have 2 unpaired electrons, 2.16 unpaired electrons, and this reduces to 0.20 unpaired electrons. So we can completely quench the unpaired electrons by adding an extra benzene ring. And the idea is that, we add the benzene ring where all the unpaired electrons are, block kind of this zigzag edge. And we see it in kind of, in this kind of heuristic thing, the unpaired electrons, but we also see it in the single triplet gap. The single triplet gap is 0.05 eV here, and here it goes up to about 1 electron volt. You can kind of play this game around, and that there's people study many of these different systems. I just want to show you 2 more examples. So one is if we use these things called Z-threnes, they have this interesting form that we can either have all bonded structures, but then we only have 2 sextets, or we have 3 sextets. But if we want to form 3 sextets, we also have to create 2 radical centers. And it turns out that we have the molecule likes sextets so much that it takes into account the fact that it also needs biradical centers. So then we do our unpaired electrons again, and we see kind of in our representation of unpaired electrons, the biggest blob in terms of unpaired electrons is also where we would draw the radical center if we just kind of draw this by hand. So I think this is also kind of an interesting way where we can feed back between this different valence bond resonance structures and our computations. So the next part of the story is then if we look at, they call it doped structures, or, structures where we have substitutions with heteroatoms. Then you find out, we have a tetracene and we add nitrogen and boron. And we see when you add them initially, then the nitrogen would have a positive charge and the boron would have a negative charge. Then, for example, for this molecule, we have another resonance structure where we can rewrite it so that we have a lone pair here, an empty spot on boron, and then here a class sextet. Now we have a second class where we can also write a structure without any pluses or minus, but no sextet, and we can only form a sextet when we also introduce radical centers. And then we have this last case here where whenever we have a neutral resonance structure, we get radical centers. And then we in this paper down here, you can read the whole story, but the idea is kind of if we move from the left to the right, then we just have increased biradical character. So the point of the story is that, I just think these polyacenes are kind of an amazing playground where I can draw all these different molecules and then play around with pen and paper, with valence bond theory. And then, kind of with these Columbus computations, you have the chance to connect what you drew on paper with kind of some well-defined quantity via the unpaired electrons. So let me switch gears a little bit. Now the other question is, we want to do dynamics of spin vibronic processes. So here the idea is, if we want to explore photodynamics in its most general sense, then, on the one hand, we're going to have unusual molecular structures, maybe strong distortions, bond breaking, and so on. So that means that we need multi-reference methods. Then next, for excited states, differential electron correlation is always important. N pi star states, pi star states might have a completely different description, and then things cancel out. Things don't cancel out anymore. We need, we need a good description of dynamic correlations. We need a correlated multi-reference method. Then, when we're interested in internal conversion, where we convert between different electronic states of the same multiplicity, then we need non-adiabatic couplings. And for intersystem crossing, hopping between different multiplicities, we also need spin orbit couplings. So there's quite a demand if you want to do photochemistry in general, and here again, MRCI with Columbus provides all these things, especially if you couple it to integrals from open Molkas for spin orbit couplings. So, and then, once you have these ingredients, there's different ways to do dynamics. We heard kind of the idea of quantum dynamics, wave packets, MCTDH. So that's what we kind of heard from Miguel. Then a nice thing is that you have that you can induce quantum effects, but you need this model potential, so you have reduced dimensionality. Then the other thing that's very popular is ab initio surface hopping, where you have to propagate things classically, but you can use the ab initio potentials and full dimensionality. And of course, both of those things are used a lot in the context of Columbus. The other option that people work on is where you all these methods of direct dynamics, variational, multi-configurational Gaussians, or multiple spawning, or exact factorization, where you kind of try to get the benefits from both methods. But actually kind of the approach that I'm trying to push is on the lower left, so that we do surface hopping with model potentials, with vibronic coupling model potentials, linear vibronic coupling model potentials. And the idea is that, that we just get this very efficient dynamics method. So it's just, LVC here means linear vibronic coupling models. And this just produces really cheap approximate dynamics method. But if you think about it, if you run surface hopping on model potentials, then it's no worse than either using model potentials or using surface hopping. So you don't introduce any problems that weren't there by either this method or that method. So, and it turns out that this is reasonably well applicable to rigid systems. So we played around with this in 2019 initially, and then from the Gonzalez group, they worked on a lot of transition metal complexes. And it's not perfect, but it's better than doing nothing, or better than just static calculations. So the one hand is, we can learn about rigid systems, are also kind of a nice way to benchmark surface hopping, because then we have then we can define the potentials in exactly the same way that we would also do for quantum dynamics methods. So yeah, to just give you a quick idea about the equation. So linear vibronic coupling means our Hamiltonian is our ground state potential plus a matrix with the vibronic coupling terms. And yeah, so it's a Taylor expansion, and linear expansion means that we just only include the first order terms. What are the first order terms? So the 0th order term is the vertical excitation energy here. And then the first order, diagonal first order term is the gradient, and the off-diagonal first order term is the non-adiabatic coupling vector. So again, if we have gradients and non-adiabatic coupling vectors, then we can get this whole linear vibronic coupling model from just one computation. So that's this kind of nice thing. You optimize the geometry, you get your Hessian, and then you do one vertical excitation with gradients and non-adiabatic coupling, and you have your whole model where you can run approximate dynamics. And of course, you can refine this later. Or if you don't have non-adiabatic coupling vectors, then you need 3n computations, like a numerical Hessian. And just, one idea, again, we're going back to MRCI with Columbus. Here the question is sulfur dioxide molecule. There was a lot of discussion in the literature about which triplet state is populated, and you can see in the upper left, this is the full MRCI simulation, and then on the upper middle, that's MRCI with the vibronic coupling model. And you see that we kind of get the same qualitative picture in terms of which kind of triplet state is populated, how the other states oscillate. And this is just so incredibly cheap because we just run this one single point computation and get all this. And then what you can see here is then we can compare our surface hopping directly with multi-configurational time-dependent hard tree with wave packet simulations, because we have exactly the same potentials, and then we can see, okay, same qualitative dynamics, but probably more oscillations with these quantum dynamics. And just to give you an idea, so we also wrote a whole paper about this, but then we can try tuning some of the mechanisms, like the velocity rescaling, some of the details of the method, and see how well they perform. We can go to higher electronic structure method. We can see what is MRCI singles and doubles versus MRCI singles. Is that better? So just to kind of give you have this amazing playground where you can test things that you couldn't test with on-the-fly dynamics. Or the other example here is, we compare adenine and 2-aminopurine, two isomeric molecules. We just move the amino group from this side to this side. And again, kind of this model shows you adenine decays on an ultra-fast timescale, 2-aminopurine has this longer lifetime. So we can, make some clear predictions about things that really matter just from these simple models. And and also these are MRCI computations in Columbus. So to conclude this talk today, so Columbus has this large-scale parallel MRCI. I showed you about unpaired electrons in polycyclic hydrocarbons, but of course there's many other different kind of complicated systems that you can treat with that. With gradients, non-adiabatic couplings, and spin orbit couplings, we can do dynamic simulations. And we've recently produced an open source release that's available for everyone. You can download it to use it. You can download it to play around with the source code. What are some future plans? So one idea is to kind of, the CI vector ends up being this huge thing, with 1 billion configurations. Then every CI vector takes about 10 gigabytes, and you want to keep them in memory. But, you need an expansion space with maybe 20 vectors, and you can see that this kind of the memory just kind of blows up in terms of storing and communication. So we're thinking about compressing the CI vector, and there's some nice ways where you can directly do this inside this graphical unitary group approach formalism. Then I guess something that's more standard is that we want to use Cholesky decomposition to deal with the integrals. I mean, the kind of the integral engine from Open-Sourece is already there, so you just have to plug it in. Something that I usually talk about is this wave function analysis methods, and of course I also want to make those available with Columbus, where you can deal with strong correlation and double excitations, the things that are usually very hard to understand. So rather than just doing the unpaired electrons, that we can delve deeper into strong correlation. And finally, something we're working on also is kind of, that there's always this problem with describing ionic states with CASA-CF and all the multi-reference methods by extension. And so we're thinking about how can we, add a tiny shift that just affects this one problematic term, and you can do this in exchange repulsion. So these things are what's currently going on. And so just give you some of the name of the more recent Columbus developers here. Okay, then thank you for your attention.
Thank you for the great talk. Now we are open for questions.